Good morning and welcome to Maastricht University's Aula. My name is Teun Dekker and today I will be representing the Rector Magnificus of this university, under whose authority the doctorate will hopefully be conferred in a little bit more than an hour's time. Thank you all for being here, especially for people who have come from far away. We do realize that Maastricht University is a little bit in a corner of the Netherlands, and that's why we particularly appreciate it when people come to see us in person, especially for such a important and festive occasion, such as a PhD defense. These booklets, they might seem thin and you might see them sort of like small objects, but I think we all know that they take an awful lot of grit and determination and inspiration and damned hard work to will into existence. And while this is indeed a formal ceremony and there will be an interrogation and opposition, in the end we always need to keep in mind that this is a celebration of work that has been done and science and the miracle that it is. So I invite you all to well, sit back. Make sure, please, to turn off your phones, because nothing is more annoying than when you're in the middle of swinging, you're really having a flow of thought, and then a phone goes off. So please turn off all devices and enjoy the show. Hereby, I open this academic ceremony in which Ayatri Singha will defend the academic thesis Gravitational Wave Astronomy with Current and Future Generation Detectors. Dear candidate, may I invite you to present a summary of your study and of the conclusions of your thesis to this audience.
Dear Prorector, committee members, supervisors, family and friends, thank you for joining at my PhD defense. Today I'm going to present a brief summary of my PhD research on the topic Gravitational Wave Astronomy with Current and Future Generation Detectors. Gravitational waves are the ripples in the space-time, curvature of the space-time that is generated by heavy and compact objects like binary black holes, neutron star. In this picture, we see two binary black holes are orbiting around each other, and the ripples in the space-time is generated, which is then emits as the gravitational waves. When a gravitational wave passes through this space, it stretches and squeezes into perpendicular direction, as it is shown here. And this effect can be detected by using gravitational wave detector, which is a laser interferometer. So from the laser, we see the beam is falling on the beam splitter, and it is then split into two parts. One part is going along one direction, another part is going along the perpendicular direction, and then it recombines at the beam splitter and is detected at the photodetector. So if there is a change in the length between these two directions, that will be detected by the photodetector. Using this principle, the gravitational wave detector works, and we have already currently operating detectors like LIGO, Virgo, as shown here. So these are currently operating. Also, we have planned for the future generation detectors, like third generation detectors, which is like Einstein telescope or cosmic explorer. They will have a better sensitivity compared to the current detectors. On 15th of September 2014, we have made our first ever detection of the gravitational wave that has been generated using the two binary black holes, as it is shown here. And this was our first detection using the current detectors. And since then, we have made almost a century of detections using our detectors. That has opened a new field in the gravitational wave astronomy. So today I'm going to cover this topic. So first I will discuss a noise, like specifically Newtonian noise for the current detectors like Virgo, and then I will go through some figure of merit analysis for different topology of Einstein telescope, triangular versus L. And then if we consider a triangular configuration of ET, then there is an advantage that we can accurately model the gravitational wave data from the detector output. So that I will also discuss. So when we see the detector output, that doesn't only contain the signal, but the noise can also mimic a gravitational wave signal. So what we see at the detector output is the gravitational wave signal, which is buried into the noise. So here we see a picture of the interferometer where we have different components that is associated with different noise, as it is shown here. And if we want to see that how big different noise is, then we can see this picture where along the y-axis we have the amplitude of noise, along the x-axis we have the frequency, and at different frequencies, different noise is dominant. So among these various noises, I have only studied this, the fluctuation of the local gravity that is associated with the interferometer in the low frequency, where we are expecting to detect some interesting astronomical events. So what is this Newtonian noise? So Newtonian noise is associated with the gravity pull that is acting on the test mass. So if a seismic wave is propagating through the ground like this, then we see at some places the density is higher, at some place the density is lowered. That means there is some density fluctuation that occurs. And due to this fluctuation, we have also a fluctuation of the gravitational pull that will act on the test mass and create some unbalanced force on it and make it move. And that is where the Newtonian noise is arising. Now, how to reduce this Newtonian noise? We cannot reduce the Newtonian noise directly because we cannot shield the gravitational pull that is coming from the surrounding. But we can do one thing. We can reduce the density fluctuation by creating some kind of structure, this kind of structure in the ground. So we see we are taking some part of it or making kind of a recess-like structure that is subtracted out from the ground, and that is how we are reducing the density fluctuation. That means we can reduce the Newtonian noise. And there is a standing example of this technique, which is Virgo. So for Virgo, we have seen that there are already recesses under the test mass. So if we see this picture here, where we have, so this is from where the test mass installation happened, and underneath this test mass, there is nothing. So it's kind of this empty space that is there. So we can consider this as the recess under the test mirror. So previously, when we have estimated Newtonian noise, this recess was not included into the model. So I have included this particular shape and structure of the recess into the model and found what is the Newtonian noise looks like. In this plot, I saw the Newtonian noise level. So the blue spectrum is the Newtonian noise when you assume a flat surface. Now, if you consider a recess under the test mass, then we have this olive green spectrum. That means it is reducing compared to the blue one. So it is showing the result that Newtonian noise can reduce with this kind of structure under the test mass. Here I have made assumption that seismic field is isotropic and also its velocity is constant, which is 250 meters per second. Well, seismic velocity has important role in order to get how much maximum reduction we can achieve in the Newtonian noise. If the velocity is lowered, that means the wavelength will be shorter and we should get more reduction in the Newtonian noise. So when I have studied the seismic data from the Virgo, I found that velocity of the seismic field is lowered, like at 10 hertz, it is below 100 meters per second. So I used new velocity estimates, this one, and into the model, and included the recess also into the model, and then found what is a new Newtonian noise curve looks like. And this looks like this red spectrum, which is even lower than the olive green one. That means it is more reduced. So quantitatively saying, we have achieved almost a factor of 10 reduction on the Newtonian noise compared to what we have if we have a flat surface. So this is serving a perfect example for the future surface detector if we want to plan it in advance, how precisely the shape of the recess should be, and to get the optimized result for the Newtonian noise suppression. Next, I'm going to talk about a different topic, which is what configuration Einstein's telescope should follow. Like it should follow L-shaped or triangle. It is proposed that Einstein telescope will follow a triangle like this. Here, 3 interferometers are making an equilateral triangle with an opening angle which is 60 degrees. But there is also one option that whether it should follow L-shaped or not. So which of this topology have the better scientific result is important for the final configuration decision. And in this context, I will first discuss what is the directionality for a triangular versus L-shaped detector, and then I will compare to different topology of Einstein telescope for the sky localization accuracy in the network. So here we see the 2 different configuration of the detector. So firstly, I would like to say that the performance of the detector is not equal or like the same for all the sky direction. So if it is a triangular detector, its performance or the response will look like this, where we have somewhere we have better response, somewhere we have not so good response. Also for the L-shaped, it look like this. But interestingly, we don't have any blind spot or where the detector cannot detect nothing. So this kind of point is absent for Einstein telescope, but it is present for the L-shaped detector. So in order to give a quantitative example, I have considered the source which is isotropically distributed on the sky, and then found for each direction of the source how far our detector can see if the same source is coming from all the direction. And this plot is showing the maximum redshift that can be attained if the source is placed at optimal location with respect to the detector. And this dashed one and the dotted one present the lower limit of the redshift if we consider the 50% and 90% of the sources all over the sky. So it is showing that Einstein telescope is having the better reach compared to an L-shaped detector if we look at the 90% curve here. So then I compare 2 different topology of Einstein telescope. So in the network 1, I consider Einstein telescope as a triangle, and it is combined with 2 cosmic explorer like this. And in the network 2, I consider Einstein telescope as L, and it is combined with 2 cosmic explorer, the same network, just the topology of Einstein telescope is different. So for each of this network, I then study that if a gravitational wave coming from any direction, then how precisely we can recover their sky position. So this plot is showing, each point of this plot is showing that a gravitational wave detector is coming from that direction. And the color bar with the magnitude is showing that what is the possible error that we can get when we want to recover the sky position precisely of that source. So this means that the less the error, that means accurately we can, or concisely we can measure the position of the source. So here we see that ET triangle having the less error compared to the ETL network, which is telling us that in the network, ET triangle is performing better compared to this second network. So if we want to get some quantitative comment out of it, then we can say that what is the fraction of the sky that is recovered with the sky localization accuracy or error less than 10 square degree. So the answer for ET triangle network is it should be 56% and ETL network is 40%, which is already telling that ET triangle is performing better compared to ETL network. Additionally, if we consider ET as triangle, then we will have an advantage having the null stream. So if we see here, so if we sum the 3 signal from 3 detectors of the ET like this, the sum will be 0. So that means when we have the data from the detector output, and this null stream will contain only noise, so the signal part will cancel out. And this is only possible if the detector data is modeled accurately, because accurately modeling the detector data involves a calibration process of the detector. And if there is some error in the calibration process, then the cancellation will not be perfect, and we will have some signal that will left into this null stream. So using this fact, we can further improve the calibration of the detector itself. So this can be useful for accurately calibrating the detector. So in this context, I have generated some mock data with the calibration error, and then I try to find what will be the residual signal in the null stream that will be left due to the calibration error, and use this for improvement of my calibration model. And I observed that if ET can detect 100 of events with loud SNR or high SNR, then we can have a factor of 10 improvement in estimating the calibration parameter. So this means that ET triangle have an additional advantage, that using the triangular configuration, the null stream, we can improve our calibration model. That's all I wanted to present. Thank you for listening. And now I'm giving word back to my prorector.
Thank you for that very interesting presentation. The opposition will now be opened by Professor Marcel Merck of Maastricht University.
Thank you, Mr. Prorector. And dear candidate, congratulations with your manuscript. I really learned a lot. As you know, I'm an outsider in this research. And I learned a lot about all these noise suppression mechanisms that you're trying to develop to let the gravitational wave detectors work. My first question goes actually back to proposition number 8. And I would like to invite one of your paronyms to read this proposition, please.
The Einstein telescope is proposed to consist of 3 xylophone interferometers arranged in a triangular topology. As a result, the sum of the signals from these 3 interferometers will be 0. Hence, it will possess an intrinsic null stream that will contain the sum of noises irrespective of the direction of sources.
Thank you. Indeed, I find this a very interesting resource, this null stream, and you explained it in your talk as well. And then I looked at chapter 7, where you explain it, and then let me try to reproduce this null stream myself, and I add up the signals of these triangle xylophone system, and I just get out 0 for the signal, as you showed, but also 0 for the noise. I get 0. So then I thought, okay, I must be doing something wrong. And then I started reading in more detail your chapter, and I see there's these H plus and H cross polarization states that you use. But I started wondering, how do you define this 0 stream in practice? How do you do this? How do you get to this data of the 0 stream? Can you help me there a bit? Maybe I'm completely wrong with my assumption I get 0, but this is, I just add up, you know, L1 minus L2, and I add L3 minus L1, and I get 0 equals 0.
Okay, thank you for your kind words and question, dear highly esteemed opponent. So, yes, we get a 0 signal contribution when we add the signal from the 3 detector of ET in a triangle. It's because it's a triangle, that means the same signal which is going to be detected, the 3 interferometer, 3 detectors. And noise, they are uncorrelated. So that means the noise in one detector is independent from the noise in the another detector. So that means when we sum up these 3 detector data, only the signal part, because that is coming from outside and it's a signal, so this part will only cancel, but the noise will not cancel because they are uncorrelated. Yes, if there is some source of noise which is correlated, like some correlation between the detector, that can cancel in the null stream.
Okay.
But the uncorrelated part should be present there in the noise.
So I think my confusion is I'm always thinking of length differences, L1 minus L2, and then you're not subtracting anything, you're just adding them up apparently. So I'm missing something in the logic there, but thank you for pointing this out to me. My other question is on this, the aspect of the, if there is still time, on the recesses that you can build around. I find this very, very interesting. And I got confronted with it on page 34 in Formula 2.1. And also you addressed that in your presentation. I see this, it has an exponential behavior with the exponent minus the height, which is the size of this cavity. And then initially I thought, look, it's gravitational field, maybe it's a 1 over r squared, with a squared in the height, or linear, I don't know if it's a big surface. Can you give me a feeling why this goes exponentially, just as a physics concept? Or is it something that you just have to calculate in detail and it comes out?
No, I mean, the amplitude of the surface wave is decaying exponentially with respect to the depth. So, I mean, if I can refer one picture here, so maybe if we look at the page 55, so here, yes, so here we see that the amplitude is decreasing with the depth of the field. So yes, it is with the height, it is decreasing exponentially.
Exponentially, okay.
Yes.
Okay, thank you. And then you showed in figures 2.5, 2.6, 2.7, you made a comparison between the areas for Einstein telescope of Thesis and Sardinia. And then I see that Sardinia is performing a little bit better in the noise, performance. And I wonder, can you compensate that by making a big cavity around the Thesis area to compensate for this difference? But I got a little bit worried because somewhere you say that page 69, I believe, you need cavities of the 100-meter size or so. And then is that something that you're thinking of how should I see this? Can we compensate this Thesis versus Sardinia in this respect?
Well, this kind of recessed structure is especially useful when we are talking about the surface detector, because for the surface detector, the velocity of the Rayleigh waves or the surface wave is lower, like 250 meters per second, and we might need only 6 meter or 8 meter cavity length for the surface detector. But when we are coming to the underground detector, there, the main contributor is not the surface wave, but the body waves that propagates through the volume. And in that case, the wavelength is much longer, which the velocity is longer. So of course, we need a bigger cavity for that. So now it is really matter of the site. Like if we consider it in Sardinia or in here, so what is the velocity there? So depending on that, how big cavern or recess we need to make. Also, the recess will not be like this. Also, it should be like a circular, because now the gravitational fluctuation can come from the whole volume. So I think, and also also there is a cost function, so we cannot make such a big cavern. So we are not thinking of that as a possible solution for this. Rather, what we are thinking, like to decrease some of the noise, the surface noise that can propagate underground. Okay.
So I tried to do it back of the envelope, and I thought I needed to compensate just by looking at the graph, 30% of a wavelength, and then the wavelength is probably hundreds of meters, so it's probably huge. And it's not very practical, I think.
No, that is not very practical, because Einstein telescope will already have a length which is 10 kilometers each side. So
okay. I thank you very much for this discussion, and I give back the word to the prorector.
Thank you, Professor Merck. The opposition will now be continued by Professor Chris van den Broek from Utrecht University.
Dear candidate, I also enjoyed reading your thesis. It has a lot of different topics in it, which is very nice to see, a lot of variation. Nevertheless, I had a few questions. Turning to page 134, there is an equation 6.11 where you define your estimate for the air-solid angle in terms of a Fisher matrix. So the first thing I'm wondering about, in the case of modeled sources, is this Fisher matrix a 2x2 matrix based only on the two sky position angles? Or is it a bigger matrix?
Thank you for your kind words and the question, dear highly esteemed opponent. So I think it should be 2x2 matrix because the Fisher matrix is estimated by assuming that how many parameters are there that we want to calculate the uncertainty of. So I think if we are only measuring the theta and phi, where from the source is coming, I think that should be 2 by 2 matrix, as per my knowledge here.
I disagree because actually if you only do a 2 by 2 matrix and then base your estimates for certain parameters on that, then you're ignoring correlations with all other parameters like the masses in the case of binary black hole signals, the masses that will be there, the time of coalescence, phase of coalescence, etc. So you will be underestimating the uncertainties actually. Do you have a sense of by how much that might be?
I think, okay, so that is why this method is good when we have high signal to noise ratio. So if we consider it's high SNR, I think then we can somehow ignore the other parameter uncertainties.
I think that's something to be proven, and I'm not sure it was, but okay.
Yes, also, it's also some question which I also am not sure about that, if it is good enough that we ignore uncertainty on other parameters.
Fair enough. So then turning to figure 6.7, right-hand panel, in that sky map, there's an enormous amount of structure, and that puzzled me because, at least geometrically speaking, the network you consider is simple, right? So do you know where all these bands and all that structure comes from?
Okay, so if I understand your question, like what is making this two thing different, right? Like why they are looking...
By the complicated pattern.
Yeah, okay. Yeah, it really depends on the plane of the detector. And if we now want to see why ET triangle has this kind of accuracy than ETL, then I think for the unmodeled source, we project the data into the null space. So the number of null stream that can contribute to the overall estimation of the sky location. So in case of ET triangle, we have 3 detectors and also 2 combined with the 2 CE. So that means we have total of 5 detectors. So we should have 3 null stream. And so one of them is intrinsic null stream. So basically 2 null stream that can contribute to the sky location. And in the second case, we have ETL and 2 CE, that means 3 detectors. So we have only 1 detector that can contribute to, or 1 null stream that can contribute to the sky location. I think that is why this pattern looks so different. So 2 versus 1. And another thing I want to add here is that ET is a triangle. And so it has, as I said, that like the figure of merit, or the figure of merit analysis, that this triangle has no blind spot, and also the performance is better compared to L.
Okay. Do you have time for one more? For plots like the ones in figure 6.6 or 6.7, no, let me actually focus on the modeled case. In 6.2, you mentioned 10 solar masses. For the modeled cases, is that the mass, total mass that you assumed, that you actually worked with to produce the plots?
Sorry.
So the only value for mass that I found in chapter 6 was 10 solar
So
masses.
are you referring to figure 6.2 or?
6 point, well, the results for the modeled case, actually, the solid sky angle.
Okay,
error.
okay.
What masses did you assume for the modeled case?
I assumed, if I remember correctly, it should be 10 solar mass. That is also written here. So I assume the same source for assuming that in one case it is modeled and in another case it is unmodeled.
Right, but why that choice actually? Because the reason why sky localization is of interest is mostly in the case of electromagnetically bright sources, yes. Right? So why did you not consider binary neutron star masses?
Can you repeat one?
So the mass for the modeled case, the masses you chose were 10 plus 10 solar masses,
yes.
But those are well into the binary black hole range,
yes.
Right? So,
yeah, okay.
But if you want to localize things on the sky and give interesting information to astronomers, then wouldn't it have been more natural to have chosen binary neutron star masses like 1.4 solar masses, and because for the same SNR you will have way more cycles in band, which would make for better accuracy. And secondly, they are the sources that are expected to be EM bright.
Yes, it can also be chosen, but this is, I have just chosen binary black holes, but yes, indeed, if we can also choose for the binary neutron stars, then that will also show this kind of like plots that we can get with using that kind of particular signal. But here I just analyzed the binary black holes.
Fair enough. Do I have time for one more? One more. Okay, good. So now going to page 101, where you combine the outputs from the LF and HF detectors. I have a question about the transition from, on page 101, yes, a transition from equation 5.4 to 5.5, where there are a number of things you neglect. So you say, we assume that the noise from the high frequency, low frequency interferometer is uncorrelated, fair enough. Mm-hmm. But what you also neglect, but you don't say why, is the inner product of signal with either of the noise streams. Now, those inner products will not be zero. It is true that they will be smaller than the remaining terms by some factor, but do you have a sense of what that factor is?
No, I can say that it should be, I mean, if we now, I think if we have a longer data stream, then I think this factor should be a factor of 10 or 10 times smaller, depending on really the correlation. But I'm assuming here that there is no correlation between the signal and the noise.
But where does the factor 10 come from? That I don't understand.
So the noise is having the zero mean. So I think if we now consider that signal also, like the signal is long enough, so the data that we are observing is long enough, I think we can, if we take now the integration, that should have some factor less. Or kind of if we find this inner product, because they are uncorrelated, that should have some factor less compared to the, yeah.
But why the factor 10 that you mentioned?
So it's I'm guessing, it's not like an exact number, but yeah.
Okay.
So I have ignored this term because I have assumed that signal and noise is uncorrelated. So, and noise is zero mean, that means that when we take this inner product, because of the zero mean of the noise, it should have a factor less than the other terms.
Mm-hmm. Okay. Thank you.
Thank you, Professor van den Broek. The opposition will now be continued by Professor Frank Linde from the University of Amsterdam.
Thank you. So, dear candidate, also my compliments with this very nice and very readable thesis. And it also addresses two topics which are close to my heart, the Newtonian noise and the sky localization of the future detectors. And what I really appreciate is that you limit the ET options to a single site thing. So no two ETs, which I think is not very realistic. And I'm happy to observe that you also do not address this. Now, of course, I have questions. And my first question goes about page 143, about the sky localization. And I must admit, personally, I think the detection capability is much more important, but the sky localization, of course, is of interest for our astronomy colleagues. So I have a question about plot 6.10, where you compare the network with Cosmic Explorer and 4 options for ET, triangle and 3 Ls. And you conclude that the triangle is superior, very good, at least better than the 15-kilometer L. I can also look at that plot, the plot on the top of page 143, and I could also conclude there is hardly any difference, because these 4 lines there, they're basically smack on each other. And my question to you is, did you also consider, for instance, a 5-kilometer ET, or even worse, an L, 5-kilometer L, or even worse, a 3-kilometer Virgo ET? And does it then really deteriorate very much? Or alternatively, did you consider smaller sized Cosmic Explorers? After all, 2 times 40 kilometer is very demanding. I think the bottom line in the States is 40 kilometers plus 20 kilometers, so not 40 plus 40. But I would like to see when it starts to deviate, okay? Because I have this impression that this plot is very much dominated by the two cosmic explorers, and not so much by what we do here in the Europe. So please comment on that.
Thank you for your kind words and the question, dear highly esteemed opponent. So yes, the comment is really useful, because I think it's if this looks like it's dominated by the two cosmic explorers which have the 40-kilometer arm length, and ET topology. So I think I have considered once, but it's not described in this dissertation. So yes, there would be some difference, but I cannot confirm right now this fact. Of course, it would be interesting to study that, but I think I can fit into this and can analyze more. So it's of course a point for the further,
Okay, now we still have time because we are not yet digging jet tunnels, so that's good. I have on the same page I have another question, also something very close to my heart. You say below that plot, this calculation focused on short duration signals, and I did not account for the effect of Earth rotation. I understand, of course, if the signals are short and the Earth doesn't rotate much, but I'm extremely interested in that Earth rotation effect. I even asked it to some other experts, Marika Branchesi, who you mentioned in one of your references, to investigate this, because I would have very high expectations of the Earth rotation effect, because it basically, it rotates, of course, the blind spot for an L. And as my colleague pointed out, neutron stars are the ones of interest. They last very long, so you get a serious effect. Now, you did not address it, you clearly say this, but could you still comment on it a little bit? And then I also would like to know whether you can include it in this fancy Fisher matrix thing. All I read is the Fisher matrix for beginners on the web, so I'm not an expert in Fisher matrices, okay? But so could you give your view? Do you think this is very promising?
Yes, that is, of course, one reason why I didn't consider the binary neutron star, because it will then, I have to start at very low frequency, and the duration of the wave will be really large, and then I have to consider the Earth rotation. So in that case, we can numerically model them, and we can numerically analyze what would be the accuracy. And of course, if we consider the rotation of the sky, the result shows that, not my result, but the other literature that I have followed shows that it is improved. So we can improve the sky location. So I think that's, and the calculation that they made was numerically and not by the Fisher matrix. So these Fisher matrix expressions I have already taken from previously published literature that was like, so I have followed this method. Yeah, but for neutron star, if I include the Earth rotation, then this formula will not work. So okay. I have to find out what is what is the accuracy using a numerical modeling. Yes, numerically.
Okay, now then I want to go to a completely different topic. We were already talking about neutron stars and the possibility to detect. And what I really am intrigued with, you mentioned on page 10 the two, let's say, fabulous events we detected. The first one, the black hole merger, and the spectacular neutron star merger. You mentioned the signal-to-noise ratios for those events, and you mentioned the false alarm rate. And the funny thing is that the black hole merger has a lower SNR than the neutron star event, but it has a higher false alarm rate, meaning it's less likely to be a false alarm. And I'm a bit simplistic here. I would think higher SNR means lower false alarm rate, but that was not the case for these two. So what am I doing wrong there? You understand? You get what I'm addressing? I think high SNR means very low false alarm rate.
So you are meaning the neutron star, which is GW170817 has okay. So it means that also GW170817 we have this multi-messenger observation. So from there we can already have the confirmation that we have detected a gravitational wave. So I think that is also contributing. Also we can, if we have multi-messenger observation like EM counterpart, then we can also pinpoint the source, where from the source is coming. And yeah, that is giving us, even for the low SNR, we have a, so I'm guessing that, I'm not an expert in estimating the false alarm, but I am guessing that is why it's the confidence level is more for the binary neutron star.
Okay, so it's additional information which is included. Okay, that I missed completely. Okay, now that explains it, I think, because highly unlikely if completely different observatories detect at the same time the same thing. I'm looking at my chair. Can I go on? Okay, then I would like to go to figure 3.7 on page 63. And there you compare three different integration volumes for your Newtonian noise reduction factor. And yeah, the interesting thing is, again, I have the feeling those three curves don't differ so much, okay? They look to me, yeah, all roughly the same. So my question is here again, did you also go to even higher volumes to integrate, or even better, to a smaller volume to integrate, to really see that it starts to deviate? And I would naively expect it should start to deviate first at the low end, which I'm honest, of course, the green one does at the very beginning, but yeah, it goes down and it goes up. It's a bit erratic there, I think. So what would be your thought on that? It would be nice to go to smaller volumes even. It makes it easier to calculate.
Yes, but when we consider the small volume, which is 30 by 30 into 15 meter cube, then we see there is a deviation for the lower frequency. So that means for the low frequency, we need more volume. But because low frequency, we have the wavelength, which is longer. And if we have a higher frequency, then the wavelength will be shorter. And in that case, we need less volume. So we can also adopt some approach, like for when we analyze different frequencies, then we can also vary the volume that is indicated by this plot. And this plot is also indicating that if we have like a 50 by 50 into 25 meter cube volume, that means we can approach almost the final result, because that result has the more accurate than the green one. So yes, it really deviates, and it depends on the wavelength of the wave, like seismic wave that we are analyzing.
Okay, thank you very much.
Thank you, Professor Linde. The opposition will be continued by Dr. Gideon Koekoek of Maastricht University.
Hi, Ayatri. Dear candidate, thank you very much for going through this journey and standing here today. I was very happy to be in this committee because it gave me the opportunity to learn about things that I don't see every day, so I read your thesis with interest. It also means I have questions. Some on the investigations of the Newtonian noise and some of the data analysis, and we'll see how far we get. So as a warm-up question, it's about the Newtonian noise and the Rayleigh waves. You mentioned on many pages in your PhD thesis that initial investigations took the Rayleigh waves to propagate with a velocity of 250 meters per second. And that number was taken from the LIGO site. Now, I looked up what constitutes the velocity of a Rayleigh wave, and it's the density of the soil and the elasticity, and then the square root of it. So how can you incorporate the number from a completely different location on the Earth and take it to Virgo and do the calculation with it?
Thank you for your question and comments, and your question. Highly esteemed opponent. So yes, I have adopted the value from the LIGO site, because at that point I haven't analyzed the seismic velocity that is specifically for Virgo. And then after, so I mean, the concept was to check if this recess exists, can we reduce the Newtonian noise? And if we can reduce the Newtonian noise, how much? So, and this gave us a very interesting result that we can reduce a factor of 2 by introducing this kind of recess under the test mass. So, so now when I have studied detailed seismic characterization for Virgo building, and then I saw that, well, the velocity is even much lower. So this means that we can have more reduction. So I mean, yes, it's true that how can I adopt the velocity from two different sites, but yeah, that looked reasonable. Like this is kind of the range when we see for the speed of the Rayleigh wave, but site-specific study shows that the soil in the Vargo site has lower velocity than 250.
Yeah, it's about twice as slow, I think
Yes,
it is.
yes, yeah.
Okay. Thank you for that. I want to follow up on that a little bit. If I go to page 90, figure 4.14, here you take your dispersion relation that you have found and that you've used to look at the strain noise. And, well, I can see that with a recess and without a recess, it has quite an effect on the mirrors, but not so much on the test masses. If you look at the upper two panels, I see that with and without recess, those two lines really start to deviate for higher frequency, and I don't see that same level of increase of deviation for the two lower panels. So what constitutes the difference?
Yes, because, okay, so for the end test mass and for the input test mass, the recess structure is not the same. So the factor, how much it will reduce, will really depend on the recess, the dimension of the recess, and also its structure. So for the central building, it is more like irregular. So it's not regular rectangular structure like end building. So this is not symmetric, and this antisymmetric thing is still reducing because we are removing some of the dense part or density fluctuation from near the test mass, but it's not as good as the end test mass.
I see. It has to do with the dimension, so to say, of the recess.
Yes.
I see. Okay. Thank you very much. Moving on, if I go to figure 4.10, which is your dispersion relation on page 84. And I want to contrast it with figure 4.13, which is a few pages later. And in 4.13, you investigate the gravity perturbation when you have the dispersion and without the dispersion. So without the dispersion and no recess, then excuse me, I'm reading this wrong. At the moment that you have no recess, then you get the dotted line in it, the purple dotted line in 4.13.
Yes.
And at the moment that you put the recess there, then you go to the green line. And, well, an interesting thing is that all of a sudden I see a certain amount of choppiness appear in the green line. The dotted line seems to be very smooth. The green line seems to be choppy. And I'm curious where the choppiness comes from.
I think it is coming from the velocity because at the different frequency we have different velocity.
Yes.
And that has been included in the green line, but in the blue line there is only constant velocity, and the wavelength changes smoothly.
Yes.
With respect to the frequency. And now when we have different velocities, the velocity at the low frequency is not same at the high frequency. That means wavelength also have a more changing pattern in case of green spectrum. So I think that is where it's coming this kind of
Okay, that's what I thought you were going to answer, and this is why I wanted to contrast this with figure 4.10, because this is where you show your dispersion relation. And there I see that between 10 and 20 hertz, the velocity hardly changes at all. There are small bumps and dents, but the locations of those bumps and dents and those frequencies do not match up with the ones in your green line. So I wonder how much of the dispersion relation causes the choppiness, and maybe some of it has to do with the numerics of your finite element method.
That may be one point, because I also have so in this case, because the velocity is very low at let's say about between 10 to 15 hertz, so that means the region of the integration should be lowered, but also the density should be higher, because it's the density of the grid point should be higher. So I have changed the density, although, but I think I have also checked with the different densities and then confirmed that this is like kind of a small change that may happen due to the density, density of the grid. So it can also, there is a probability that it can also appear due to the not the boundary, but the points, the number of points that we consider into the model.
I see.
And we have done this for really good density, but yeah, that I cannot immediately comment on just by looking at this.
No, I understand. It's quite striking at particular points. For instance, at 13 hertz, there is a sharp increase in the green line, and I don't see this in your dispersion relation, where it seems to be quite flat at that stage.
Just to say that in this case, here I would like to mention the green curve has been generated by these blue dotted points. So in the 4.10.
Ah,
okay,
I see.
And this is the best fit one.
I see. Okay. Oh, thank you very much. That clears up a lot. I was going with the black line. I thought that was the one that you were using.
No,
okay.
this black line is kind of a fitting, like this is how the trend is following.
I see.
But I have used in my model, I have used these blue values for the speed.
Okay, that makes me happy. Then it shows that I'm not crazy. Thank you very much. Professor Dekker, do you have time for one more? A very short one. This has to do with your usage in chapter 7. Let me go to the right page for you. Give me a second. Yes, it's page 165, where you use a Fisher matrix formalism to investigate calibration errors using the null stream. And on that page, you leave out that your calibration errors potentially could have a time dependence, and I understand that. But later on, you mention that you have to build up a whole lot of 200 or so events in order to do the calibration analysis, and you also have to have loud events. So I would think that takes more than short snippets of information. So my question is, does your assumption of the time independence of your calibration errors hold if you have to wait until you build up about 200 loud events before you can do the analysis?
Yes, that will depend on the performance of the detector. Yes, there are some parameters which have the time dependence itself, and also there is some like parameters can drift with time. But what we usually assume is that it can have the at least for a time span of weeks or so, we can assume that we can take the events from those the time data. Let's say if we take 100 events for ET, because ET is expecting to have more detection because its sensitivity is better, it can have a better reach. So if we have more events, then we can do better in the calibration modeling. So that is the point here that that is being considered. So currently, because we haven't built the detector yet, so we are expecting that it should have a period of weeks, like 2 weeks or 15 days maybe. That I'm just saying this out of the intuition. So that this can have the assumption can hold to some extent. So of course it's not fully that it's the time. Like I'm not putting any bound on any parameter, but I'm expecting that overall pattern should look similar to for this time span.
Okay, so paraphrasing, you are assuming now that the calibration errors will be stable for the order of magnitude for a few weeks.
A calibration or the model of the interferometer. Sure. So it's a response function, let's say, how the interferometer responds. So calibration error is appearing because we are assuming a calibration model with some parameters that might not match with the actual calibration of the detector. So yeah. So calibration error can be different. So maybe there is 2%, there is 3% error. That's fine. But if it is like the model response function is the same, that is the main point here.
Yeah, you corrected me correctly. I should have said model, but thank you. I have more questions, but I think we can have a private discussion later. So thank you very much for the discussion, and I give the floor back.
Thank you, Dr. Google. The opposition will be continued by Dr. Jessica Steinlechner, also of Maastricht University.
Yeah, dear candidate, congratulations also from my side for this nice work, and thank you actually. So I was wondering, in this graph here on page 14, where you show all the different noise sources in the example of LIGO, and which you also have shown in your presentation, we can clearly see Newtonian noise and how all the other noise sources fit in. But later on, when we look at ET, that is here on page 100, where you show the different ET noise curves. Here we cannot actually see what noise curve or how these noise curves are decomposed into all these different sources. So in which frequency range do you actually see here Newtonian noise to be dominating? So up to which frequencies?
Thank you for your kind word and question, dear esteemed opponent. So yes, for the low frequency sensitivity of ET is limited by this Newtonian noise. So it's not shown here in the dissertation, but I think below 15 Hz we expect that this is limited by the Newtonian noise, and so that is why we have the plan to go underground, so that because the surface seismic waves, they are having bigger amplitude, but when we go underground, the amplitude of the seismic field is lower because their amplitude is lower, but there will be the noise that will still be there will limit the low noise sensitivity of ET, because there we are aiming for a factor of 10,000 improvement at the low frequency. So in that case, yes, it's a big noise source for ET underground.
Okay, so, and you said now 15 hertz roughly, so this is already a little bit higher in frequencies here compared to this little I don't know, kind of curve here where the green and blue lines here make this curve. So, I mean, as you know, I'm usually mainly worried about coding thermal noise, and several other people in the room here are worried about it very much too. So, what would you say? How much should we further reduce this noise? I mean, the goal for coding thermal noise reduction is about a factor of 10 compared to, or actually taking into account the longer arms, a factor of 25, so that it's not dominating the noise curve at all anymore. But how much does it make sense, in your opinion, and where would we be not dominated anyway by Newtonian noise? So in which frequency range do we have to continue our work?
Yes, I have a plot. That's the published one, published from paper. So it's page number 48. If you see here, we have what is the sensitivity curve of ET at low frequency, and here we see for different site, target and Sardinia, what is the limit or where we are expecting to have the Newtonian noise for these two sites. So from here we can see we need, if it is target, as if we see it's a factor of 10 we need to reduce, but it's kind of of course, as I'm saying, that it's not, it's some type of assumption that has been made in order to make this curve. So based on this curve, we can say, yes, we need to improve, of course, for Newtonian noise, because it's lying over the black curve, because that's the target one, and this is what we have for the different site.
Okay, thank you. And actually, I think that's already everything from my side. So that's the fate of the last one who gets to ask questions, and my other questions have already been answered before.
Thank you, Dr. Steinlecher. The opposition will then be continued a little bit more by Professor Chris van den Broek from Utrecht University.
Thank you. I'll try to pick a not too long question, I guess, but let me return then to page 101. So where you, well, or in that vicinity, you sort of patch together the LF and HF detector outputs, and you come up with a quantity that you need to minimize and so on. But I have a conceptual question, actually. So this joining of LF and HF data, it comes with a certain amount of risk because you're modifying the data using assumptions that will not literally be true, right? So it comes with some amount of risk. But on the other hand, why would you do that, actually, the joining of the data? Because I don't see any conceptual problems with treating the HF and LF detectors or interferometers as part of an interferometer network, the same way we do with LIGO and Virgo. I don't see a conceptual problem with there being only a little bit overlap in frequency ranges. This goes for both detection and parameter estimation. In fact, I don't even see a reason why there would be more computational expense. So can you comment on that? Have you thought about that? So the question is, why not treat the HF and LF as a detector of networks, just like we do with LIGO and Virgo now for detection and parameter estimation, and be done with it?
Yes, I agree that if we have even two detectors, then we can do analysis with the two detectors, like as low frequency and high frequency one. But we can also combine. So I think this combination is kind of similar, like we are applying a low pass filter and high pass filter, so that because anyway what we want to show that this is the complete waveform from the ET1 detector, the xylophone detector. If we combine these two xylophone and want to get what would be the full waveform and how the whole noise curve will look like, so the optimal one. So this is how we can combine them. So it's kind of a message.
Ayatri Singha, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and of your defense, and I request that you and your company await the results of our deliberations and our return in this room.
Please all rise.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Southside, 10 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. All your time, 'cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even Even though these nights seem long, I know that I am never on my own. Know you won the battle once you've grown. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side, no place like home. If it's questions that you've got, go the extra mile and that. What's on the line? I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
Ayatri Singha. The degree committee here present has assessed the quality of your thesis and of your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Hilt is hereby authorized to confer upon you this academic distinction in accordance with Dutch university custom, and I now invite your supervisor to take the floor.
Please, all right.
Yeah, I realize now. Thank you. Ayatri, do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and conformity with the decision of the committee here present, I hereby confer upon you, Ayatri Singha, the degree of doctor and grant you all the rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Dear Dr. Singha, dear Ayatri, it's our absolute pleasure to congratulate you on your well-deserved PhD degree. I think it's fair to say your PhD has been a bit of an interesting journey in the literal meaning of the word journey. I still recall, well, our first Skype chat back in 2017. You were finishing your master degree in India at the time, and I was still in Scotland at the time. This was the time when we as a gravitational wave community had just celebrated and digested enough the first discovery and the saga of the first neutron star discovery. And people started to push more again on the Einstein telescope and cosmic explorer, and that was really where you were coming from. As a result of the Skype call, you applied for a Commonwealth's PhD fellowship. I'm not sure whether you still recall, to come to Glasgow, where your PhD journey then started towards the end of 2018. Actually, you didn't get a Commonwealth's PhD fellowship, but you were awarded the first Ron Drever fellowship at that time. The family of the late Ron Drever, who was one of the co-founders of LIGO, together with Ray Weiss and Kip Thorne, had set up a private fund to sponsor always at any time one PhD student in Glasgow to work on gravitational waves, which was Ron's alma mater. Anyway, so after acclimatizing from the Indian climate to the slightly different and famous Scottish weather, you became immediately very productive researching figures of scientific merit for future gravitational wave detectors, deviating from the standard L shape. That was very much at the beginning of your PhD studies, but already there, everyone involved could see the sparkle of your scientific capabilities, the enthusiasm and the full power with which you tackle tasks and which we learned to applaud you to many times more over the coming years. And then your supervisor was throwing in another interesting event in your PhD journey. As I told you, I would move away from Glasgow and go to Maastricht to start something new and nice here, and you would need, or you would be asked to decide whether you want to stay in Glasgow or whether you would join moving to Maastricht. Goes without saying, I was very happy that you decided to join in Maastricht. Yet another culture, another language, switching from the LIGO collaboration to the Virgo collaboration, and obviously all the challenges of being one of a handful of people starting a new department from scratch. I recall quite at that time communal atmosphere when our department consisted of a single big office, where we were sitting together with Andre, Viola, Sepp, who was at that time an intern from Brussels University, Gideon, Sebastian, Jessica, and Esther. So that was a quite interesting department in one office. However, then I think the biggest change hit shortly after we started here in Maastricht, and that change, I assume, must have been bigger than changing countries or weather, and that was the start of the pandemic, which turned the world upside down for all of us in similar or very different ways. I can only imagine how this must have been for you, just new in this country and your family far away on a different continent and unreachable for you. So indeed, not an easy journey you have behind you. However, in contrast to all the adverse influences from the outside, your scientific journey was very much the opposite, meaning a straight and broad avenue of success. And it was a joy to observe you on that path. The speed in which you produced new calculations and simulation results truly amazed me one time after another. We were always looking forward to our weekly update meetings, as I knew you would come well prepared with a nice set of slides showing progress you made over the past few days. Your work on Newtonian noise estimates was, I think, the first real contribution of the then newly established Maastricht group to Virgo. It really put Maastricht for the first time on the Virgo map. And also your research that in that field ended up with several publications you led, but also results still serve as today as the official Newtonian noise model for Virgo and for the coming years to be. Being able to measure the dispersion relation for the Rayleigh wave fields at the Virgo site and finding a lower than expected speed really pushed the Newtonian noise down by a bit, creating lots of new space for detector upgrades targeting low frequency end of the detection band. Maybe a little bit referring to Jessica's point here. Your analysis related to the observatory geometry in ET helped a lot to better understand the differences or commonalities between an L and a triangle detector from a purely scientific point. This was very refreshing, I have to say, in the very often very political and controversial, sometimes even polarized discussions that happened within the ET community. Your work on using the null stream information for calibration improvement, I'm sure, will lead to many people picking up this aspect and related topics and further exploring them beyond what you have started here. So, in summary, we really can only congratulate you wholeheartedly to these achievements and your well-deserved PhD degree. I think you can be very proud, and also we are very proud as the first PhD student has now graduated from this group here. Usually at this point, I would start wishing the PhD awardee all the best for their future, different jobs, a different institution, or even a different country. However, in your case, I'm very happy that you will stay with gravitational waves, and not only with gravitational waves, but with the department, with NICAF, as a postdoc working on a topic very crucial for ET and the realization of ET in our region, which is understanding Newtonian noise potentially created in ET due to wind turbines in our region and potential ways how to mitigate it. So, congratulations to you, your family, friends, and as I said, you can be very proud on this very special day.
Dear Dr. Singha, also on behalf of Maastricht University, I congratulate you with the degree you have acquired, because a doctorate is forever, and it signifies your admission to the community of independent researchers, and I have no doubt that you will use that position for our own benefit and your own enjoyment. So, thank you very much. I hereby close this academic ceremony. What happens now is that we, the degree committee, and you and your parents will go off to the staircase to take a commemorative picture.